Cool. Another product that was introduced just earlier this year by Lightning AI, and which we've never talked about on air before, we didn't talk about it in Sebastian's episode or anything, is something called the Thunder compiler, which Thunder sounds like a nice compliment to Lightning. So tell us about that.
Yeah. So somebody said, "Oh, Thunder is slower than Lightning, so why are you making a compiler that is slower?" But we stuck with the same name. Like, it's okay. Let them wonder. So Thunder is to me, it's a very interesting endeavor. It's extremely challenging, but it responds to one fundamental question. Nowadays, with the sizes of models, with the money being poured into training and inference and so on, the ability for you to run a model at its best on a given hardware for a given set of inputs and workloads and so on kind of depend on all these things together. So there's no, I have a perfect kernel. This will power everything across the board on any GPU, on any context size. We're talking about LLMs and so on. It all depends on what is the hardware you're running on, what is the memory, what is the memory bandwidth, how large are you sizing your inputs, like how much memory do you need to shuttle back and forth, and so on. And all these things, finding the right optimizations for the right configuration and combination of model hardware and so on, and inputs, it's becoming where the meat is if you want to get to train or run inference with the best possible performance. And so you can either tweak your code and hope that something will get better on the other side. But I think ultimately we're getting into a phase where we need to we need to be able to provide post source code optimizations in the easiest way possible. And by that, I mean, however you write your original model, whether you control it or not, because sometimes, I'm running a Hugging Face or, somebody else wrote that model. And then you need to decide what operations to fuse or how to manage different types of precision in the model, or how to offload parts of the computation, or throw away some intermediates and recompute them. And all these decisions are so dependent on a combination of things that the ideal is that you have your computation expressed in a way that is amenable to be transformed either manually or programmatically into something else before you get it to execute. And then even executing it, you can choose whether you want a set of kernels or an engine or something else that will execute it. So in a nutshell, program transformation is what compilers do. And our goal is to make it a first-class citizen of a framework. So how can you write a framework so that program transformation becomes something you do, either manually, automatically, but you have access to everything, like you can reason through it. Because right now, up until now, compilers are kind of black boxes, right? You come with your source code, you throw your source code into something that will do its thing. There you can set flags, activate optimizations that some genius somewhere wrote for you, and then you need to hope for the best. And sometimes this doesn't lead to results that you were expecting, and you're left wondering why. And Thunder is a response to that. It's still very much work in progress, but it has some fundamental things that would help you reason through what program transformation is about and what you need to do to improve your performance. Yeah.
Nice, cool. So when somebody is thinking about doing compiling, what kind of person needs to be thinking about doing that? I, as a data scientist, I have never compiled, it's been over a decade since I've compiled anything. So when might a listener want to, what are some scenarios where they would actually want to be doing some compiling? And then when they do that, Luca, what do they do? How, is it like importing something
Yeah.
importing a package? Because it's presumably something that happens outside of the context of like a notebook environment.
Well, you can actually, okay, so let's take a couple of steps back. Compiling, for whoever has used software means you have source code, you get an executable out, and then I can give you the executable, you run it. And it's not exactly about that we're talking about when you have a deep learning model. Compiling is transforming it and then coming out with an execution plan that can involve specialized kernels. It can still be in Python, doesn't need to go into C, or maybe it will go into C. So you turn it into a way where you optimize some aspects like memory usage or execution time and so on. So compiling is kind of a broad term. We call Thunder a source-to-source compiler because it doesn't generate kernels per se, but it will transform the computation so that you can then use the kernels that fit your thing the best. But when would you want to use a compiler is when you want to squeeze performance out of a single GPU, multiple GPU, or multiple machines with multiple GPUs on them. It's all about the performance. If you don't have performance problems, then probably you don't need a compiler. However, nowadays, GPUs are expensive and you need to run things that are super large most of the time. And so having a flexible compiler infrastructure is something that will allow you to get the most out of your money. But I think they're very bimodal. There is a very bimodal distribution of users. The users that do not care about any detail, and the users who actually want to go in and optimize the heck of their workload. And we're trying to address both with two different APIs in Thunder.
Very cool. So this allows you to, in a scenario like it would be common today, where you're training or deploying large language models, these take up a huge amount of GPU infrastructure. They're very expensive to be running and deploying. And so, whether you're aware of it or not before listening to this episode, it might be helpful to you and your organization to be taking advantage of something like the Thunder compiler to allow you to be making the most of the infrastructure and of the spend that you have.
Yeah, correct. And I mean, Thunder is by far not the only compiler. Actually, is one of the, if you will, less mature ones. There are, if you ever use JAX or PyTorch XLA, you can run on XLA on the XLA stack. But even before that, there's Torch Compile that was first released with PyTorch 2.0, and that's the natural choice when you want to switch on a compiler. Like, let's try to compile this model and see what the effect is. You usually torch.compile the model, and then you run the model that comes out of that, and that interprets the code and then generates optimized kernels to run the code in something called there's a dynamo and inductor, which are the two pieces of Torch compile. Dynamo capture what your code wants to do, and inductor generates optimized kernels from that. And so we like to think that Thunder is again a complement to Torch compile for certain things. And then if you've been following optimizations in LLM space, there has been a lot of hackers, right, that has gone into, let's re-implement this model in C. And so like Andrei Karpathy was much more than a hacker, of course, but he did this project called LLMC, where a lot of hackers this time joined him and optimized training for initially GPT-2 size models, all in C. So they had C, they had CUDA, and the whole stack was basically fit in a couple of files. It was great because, with a minimal amount of lines of code, you had everything. And so you didn't need to pierce through layers of abstraction in order to say, okay, let's reuse this memory buffer for this other thing, because this will allow us to save an allocation and so on. So that kind of fine granular control is what makes those projects successful, at the expense, of course, of generality. And same thing for Llama CPP and other projects like that. What we're trying to achieve with Thunder is giving you a basis that is thin enough so that you can reason through the stack without having, again, to pierce through too many layers in order to optimize your thing and to open it up to you as a practitioner.
Trying to get those principles right, as you described already earlier in the episode,
Yeah.
where you're trying to not dictate too much, not make too many assumptions about what the users are going to want to be able to do, while simultaneously offering them flexibility if they want it.
Yeah, exactly. And it's a hard balance to strike, but we're well on course, I think. We're using it internally. We're very happy with it. So